Hello all, welcome back to this lecture series on static timing analysis. In this lecture, we are going to discuss about the delays in sequential circuits, and we will also see how to calculate the setup time and hold time in this sequential circuits. So first we will start with the delays in sequential circuits. Delays in sequential circuits. So what are the delays which are present in sequential circuits? Let's see one by one. So first type of delay is called clock to Q delay. Clock to Q delay. And second type of delay is called S to Q delay. S to Q. I think we have already discussed this type of delays in our previous sessions. Just a brief brush up of this. And we have R to Q delay. R to Q delay. So these are the type of delays which we have in our sequential circuits. One is clock to Q delay, and second is S to Q delay, and the third one is R to Q delay. So basically, what is this? What are this delay? We will discuss one by one. So first one is called clock to Q delay. What is this delay? So basically, this clock to Q delay is the delay. It is a time it takes for the flip-flop output to be in stable state after a clock edge occurs. So it is a time taken by the output to be in a stable state after the clock edge occurs. Okay. So this is the clock to Q delay. For example, let's consider this as our clock. Okay, so let us assume this is our clock signal. These are the positive edges of this clock, and this is applied to any flip-flop. Okay, so input is given to any particular flip-flop like this. So let's say we are giving our input here at this particular edge. Okay, now what happens? The clock to Q delay is the time the output takes to get stable after the edge. Okay, so the output, where is the output? Let's say this is our output. After here we are applying the input, so it is a time taken by the output or the flip-flop to produce an output. Okay, so the time taken by the output to be stable after the edge. Okay, so here it will become stable like this. Some flip-flop, I'm taking a random example. So after applying the input, we'll get the output somewhere here, after here. Okay, so after some time delay we will get this output. Okay, so this is called as clock to Q delay, right? Next, coming to S to Q delay, second one is S to Q delay. So this is the time taken by the flip-flop to come to set state after the application of asynchronous preset input. So I hope you are aware of this preset and reset signals. So we in flip-flops we may also have this type of signals, preset and reset. So these are basically asynchronous signals. These are basically asynchronous signals. This is also asynchronous. What is meant by asynchronous? It is not related to the clock. Okay, there is no dependency on the clock. They can be if they are applied at any instant of time or at any edge of the clock, it will be either set or it will be equal to reset. So if we apply preset signal, it will be the output will be equal to 1, and if we apply reset, the output will be equal to 0. That is preset and reset signals. So what is this S to Q delay? So it is the time taken by the flip-flop to come to the set state after the application of asynchronous preset input. So let us say this is our clock. Again, we will consider this clock. These are my, I'm considering a positive edge flip-flop. So these are my positive edges. Now, so if I apply preset signal, asynchronous preset signal is equal to 1 at any edge of the clock or any level of the clock I can apply. So if I apply the negative edge like this, So this is my preset signal. Preset signal. Okay, I can apply it anywhere. It will not depend on the clock. It is asynchronous. Okay, so if you apply at any instant of time, the output will become 1. But when it will become 1, it will take some time to see the reflections in the output. So this time is called S2Q delay. This time is called S2Q delay. S2Q delay. Okay. So the time taken by the flip-flop to come to set state after application of asynchronous preset input. We don't know about the output in this previously, but after applying the preset signal, what time it will take to come into the set state, this delay is called S2Q delay. We don't know here what is the output of the flip-flop, or we don't know the state of the flip-flop, but after applying a preset input, asynchronous preset input, the time the flip-flop takes to produce the output, this delay is called S2Q delay. And similarly with R2Q delay, so it is the time taken by the flip-flop to come to reset state after the application of clear input. So we have reset input, or we can also have clear. It is also asynchronous input. So basically what happens, if we apply preset signal, the output will be set to 1, and if we apply clear signal, the output will become 0. So previously we don't know the output, whether it may be 1 or 0. We don't know the state of the output. So if we apply clear signal like this, if we apply a clear signal, then what happens, the output will become 0 or clear. So the time the output is taking to respond to this clear asynchronous clear input is called R2Q delay. R2Q delay. Okay, that's it. Simple definitions. S2Q delay and R2Q delay. So the for S2Q delay, it is a time taken by the flip-flop to come to set state after application of asynchronous preset input. Whereas for R2Q delay, it is a time taken by the flip-flop to come to reset state after the application of asynchronous clear input. So these are the delays in sequential circuits, right? Now let us see what is this setup time and hold time, and let us see some definitions about this setup time and hold time. So basically, the setup time is the minimum time interval for which the input signal must be stable prior to the sampling event of the clock for the input signal to be recognized correctly. So this is the definition. So I will write it also. It is very, very important. It is the minimum time interval for which the input signal must be stable prior to the sampling event of the clock for the input signal to be recognized correctly. So this is the definition of this setup time. Okay, so now let's see what is this with the help of a waveform. So before that, you can observe here the keywords, that is stable and prior to the sampling event. What is this sampling event? So the sampling event can be of any event in the clock. The sampling event can be of 4 types. One is positive edge. Sorry, it can be of 2 types. One is of positive edge and next is of negative edge. Okay. This can be any event. Positive edge, if it is a triggered flip-flop, clock triggered flip-flop. Flip-flops are basically edge triggered flip-flops, right? So it can be, the sampling event can be a positive edge or negative edge. We can calculate the setup time for any sampling event, that is whether it can be positive edge or negative edge. Okay, So the minimum time interval by which the input signal must be stable prior to the sampling event, whether it may be a positive edge or negative edge of the clock for the input signal to be recognized correctly. So what is this? This is also a keyword, recognized correctly. For the input signal to be recognized correctly, the input should be applied before the sampling event of the clock. Okay, so the input signal to be recognized correctly by the flip flop. So if we are giving any input to our flip flop, if we are giving any input to our flip flop, to recognize that input correctly by the flip flop, it should be applied before the sampling event. That's it. Okay, before the sampling event of the clock. So this input, if it should be correctly recognized by our flip flop, so it should be applied before the sampling event of the clock. Okay, yeah. So let us understand this with the help of timing diagram also. So let's say this is our clock pulse. Let us consider it is a positive edge flip-flop, positive edge triggered flip-flop. So these are my sampling events. Positive edges are my sampling events, right? Now, this is my clock. And what is the condition for this input to be recognized correctly? The condition is that it should be applied before the sampling event. That's it. That is a setup time requirement. So the input should be applied before the sampling event so that the flip flop can recognize it correctly, right? So where are the sampling events? So these are the sampling events. So I'm considering it as a positive edge flip flop. Consider a positive edge flip flop. I'm giving the input to my positive edge flip flop. So what is the requirement? The input should be applied before the sampling event. So these are my sampling events, right? So where should I apply the input? Simply, I should apply the input before the sampling event, right? This is the this is where I should apply the input. Okay, so for every flip flop there will be certain setup times. Okay, so let's say for this positive edge flip flop, this is the setup time. This small amount of period, this small amount is called setup time for this T setup. So any input to be recognized correctly, this input should be given before this time. Okay, you can observe this time, right? So before this time interval only, the input should be applied. Okay, so for this input to be recognized correctly by the flip flop, the input should be given before this time interval. What happens if we give after this time interval? Let's say this is input 1 and this is input 2. Okay, what happens if we give this input to after the time interval which is given by a flip flop, that is after this setup time? Then this input will not be recognized by our flip flop. Okay, so that's why we should give the input before this time interval, that is before the setup time only. Okay, I hope it is clear. Coming to next one, that is hold time. First I will write the definition and next I will explain it. Okay, so hold time is the minimum time interval for which the input signal must be stable following the sampling event of the clock for the input signal to be recognized correctly. So it is the minimum interval of time for which the input signal must be stable following the sampling event of the clock so that input can be recognized correctly. Okay, so what are the keywords in this particular definition? So the minimum interval of time for the input signal must be stable. Okay, this is a keyword, stable, following the sampling event. Okay, in the case of setup time, what we have? Before the sampling event, prior to the sampling event. But in the case of hold time, what you can observe? following the sampling event, okay, of the clock. Sampling event may be positive edge or negative edge, so that the input can be recognized correctly. So what happens here, let us understand with the help of waveform. So these are my sampling events, right? So these are my sampling events. So let us say this is my clock positive edge, this is my input. So to avoid setup time violation, that is the input should be recognized correctly. What I will do to avoid setup time violation, let's say this is the setup time. This is the T setup. So before this time interval only, I should provide my input. Okay. Okay, I have provided my input here. Now here my sampling occurs, okay, that is my input will be read by the flip flop, okay. Then what happens, the input should be according to the definition what it is. So minimum interval of time for which the input signal must be stable following the sampling event, where my sampling happens at this positive edge, right? So following the sampling event, the input should be constant for minimum amount of time, okay. So after the sampling event also, the input should not change. It must be stable following the sampling event. So for how much time it should be stable? That time is called hold time. That time is called hold time. Okay. Hold time. So the minimum interval of time for which the input signal must be stable following the sampling event. Here my sampling is occurring. So immediately I should not change my output. Sorry, I should not change my input. It should be stable. For how much time? That time is called hold time. Okay. So for that interval of time, for the particular interval of time, my input should be stable so that it is properly recognized by our flip flop. So immediately after the sampling, you should not change the input. It should be stable for minimum interval of time. That interval of time is called hold time. So after this time, you can change the input. Okay. It's your wish. If you want to change the input, you can change. Or if you do not wish to change the input, you can, your wish. Okay. So this is called hold time. So what happens if you are not following this hold time requirement? Then you will get hold time violation. You will get hold time violation. And what happens if you are not following setup time requirement? You will get setup time violation. Okay. So these are basically setup time and hold time violations when you are not following the setup time and hold time requirements. Right? Is it clear? Now, let us consider an example here. So let's say this is my flip flop 1 and this is my flip flop 2, right? And here I am applying my input, and this is my clock pin, this is my input pin. These are synchronous sequential circuits, so they share the same clock. Okay. Now here the output will be passed through some combinational logic circuit. It may be any combinational logic circuit involved here. So what happens? What type of delay is we will get when we have any combinational circuit? That type of delay is called propagation delay. I hope you have revisited, you have watched my previous sessions. So in that we have discussed what is this propagation delay. Okay. So when we are having any combinational circuits, then we will have this type of delay which is called as propagation delay. Okay. So this delay also we should keep in mind, right? Now, so the data is flowing from flip flop 1 to flip flop 2. what is the data flow? The data is flowing from flip flop 1 to flip flop 2. Okay, and the clock is also flowing from flip flop 1 to flip flop 2, right? Now we will not consider the case of skew. We will, okay, we will only consider what is happening here now. Let's say our flip flop one. So to avoid setup time violations, what should be considered? So we should apply this input before the setup time, before the positive edge of the clock or the setup time. So let's say our t setup is 2 nanoseconds, right? So with the help of diagram, I will try to explain. Right, so this is my clock and my setup time is 2 nanoseconds, that is before this positive edge. Sorry for my bad drawing. So this is my setup time, t setup time, which is 2 nanoseconds. T setup, that is my input should be applied before the setup time, on or before 2 nanoseconds, right? So this is my input to flip flop 1, input to flip flop 1. Let's say I'm applying it correctly, I'm following all the setup time requirements, and I'm applying the input, and I'm also following my hold time requirements. Let's say the hold time is also 2 nanoseconds. So my input is constant for 2 nanoseconds and I'm changing it after 2 nanoseconds, right? Like this I'm changing. So this is the input for our flip-flop one. So since I am following all the setup time and hold time requirements, there is no setup time and hold time violations, right? So there is no setup time and hold time violations. Now I've applied my input to my flip-flop. When I will get the output from flip-flop? After clock to Q delay. We have discussed it, right? So after clock to Q delay, I will get the output. So after the clock to Q delay, I will get the output. Let's say it's some random flip-flop. Like this, we will get the output. Okay. So after some delay, which is called as clock to Q delay, we will get our output. Clock to Q delay. After this clock to Q delay, we will get our output, right? So this output is passed through this combinational logic circuit. So after uh, this this output is passed through this combinational logic circuit. So this combinational logic circuit, what it will do, this combinational logic circuit will basically process the output which is given by the flip-flop one. And so it is the input for our combinational logic, right? So what it will do, it will process the output which is given by our flip-flop one, and it after processing and after some propagation delay, it will give the output. So the output of the combinational logic circuit is further given after this propagation delay. So I will mention this with the time period TPD. Okay, so after TPD time units, after TPD time units, we will get output from combinational circuit. Output from combinational circuit, right? So let's say this TPD is around some 2 nanoseconds, right? So let's say we are getting this output, that is input for our combinational logic circuit at, let's say, at 5 nanoseconds. So when we will get the output of this combinational circuit, that is 5 nanoseconds plus 2 nanoseconds, that is 7 nanoseconds, we will get the output. So when we will get this output, that is at 7 nanoseconds, we will get the output. Now we will consider one more case. 1 minute. We'll consider one more case. So this output is given to flip-flop 2, right? So it will become input to flip-flop 2. So this input to flip flop 2 is given at 7 nanoseconds. Here this is the input, right? So I'm drawing it. So this is the input to our flip flop. So you can observe here, this is a clock, right? So this is the setup time. 2 nanoseconds is the setup time. 2 nanoseconds is the setup time. So you can observe here the input to flip-flop 2 is given before the setup time itself. Okay. So before the setup time it is given and it is stable during the setup time. And after the sampling also the input is stable. The input is stable after sampling also. Hold time requirement is also achieved. So there is no hold time violation, right? So there is no setup time violation and hold time violation for flip-flop 2 also, right? Are you able to understand? So uh, this is how we have achieved the setup time and hold time requirements for both the flip flops. What if the combinational logic circuit has more propagation delay? What if the combinational logic circuit has more propagation delay instead of 2 nanoseconds? Let's say if the propagation delay of this combinational circuit is, let's say, somewhere around 5 nanoseconds, then what happens? Then the output will get some delay. We will get the output somewhere, let's say here. So we will get the output somewhere here. Then what happens? The input of the flip flop is given somewhere here at the correct exact positive edge. Then what happens? Then there will be a setup time violation. Then there will be a setup time violation like this. Okay, so this is how there will be setup time violation. And if the output is given let's say at 1 nanosecond and the output is changing immediately, then there will be a hold time violation, right? So this is how setup time and hold time violations occurs. Because of this there may be uh, due to the propagation delays of the combinational circuits involved in this circuits. Okay, so this is the example I wanted to show you how setup time and hold time violations may occur in the practical way. Okay, so in our next session we will discuss how to form the equations for setup time and hold time. So there will be some equations for calculating the setup time and hold time. Yeah, so in our next session we will discuss those. Okay, so I hope this explanation is clear. Yeah, that's all for this session.